Hello, everybody. My name is Andrii Mironchenko. Welcome to my Habilitation Colloquium devoted to input-to-state stability of distributed parameter systems. Distributed parameter systems, also called infinite-dimensional systems, appear frequently in many areas of natural sciences and engineering. In particular, in aerospace engineering, climate modeling, population dynamics, biomedical applications, and chemical engineering. To see the challenges that appear in analysis and control of such systems, let us consider some typical applications. The first of them is so-called event-based control of distributed parameter systems. Assume that we have any type of distributed parameter system and assume that it is unstable. And our aim is to stabilize such a system. Assume that we were clever enough to develop a controller so let's say another system which stabilizes this one. However, assume we have done it under assumption that the values of the controller can be changed continuously in time. So it's like mathematical abstraction. So it's a very good mathematical abstraction. But if we go to an engineer and tell, okay, let us implement this controller in the real world system, then he or she will tell us that it's not directly possible because we cannot update the value of a controller continuously in time. So what we can do is to update it at some discrete time moments called events, and we need to add one more component to our network, which is an event detector, which generates this sequence of times at which the controller will be updated. And now we have a question. Will this digitalized controller still solve our problem? Will it stabilize the distributed parameter system or not? So, and just think, this is a very general problem. So we have not specified what is this distributed parameter system is. So it's just a very basic problem in the implementation of control algorithms. And what do we see in this problem? We have a distributed parameter system, or actually a network with infinite dimensional components. We have disturbances acting in this system, which are due to sensor errors or errors in the action of a controller. And more importantly, we have another type of errors, which is the distinction between this idealized continuous time controller and its discretized version. So this difference can be understood as a disturbance which goes into the system. And now we need to robustly stabilize the system independently on all these disturbances. Let us consider another kind of application. So in the previous example, we have had a system with 3 components, but the real-world networks can have huge number, thousands or hundreds of thousands of components. Such systems can be manufacturing networks, electrical grids, transportation networks, social networks, etc. And emerging technologies like 5G, Internet of Things, or cloud computing make the networks larger and larger from year to year. We need to verify the safety and reliability of such networks, but unfortunately, the existing tools do not always cope with such a complexity. So our aim, in order to address all such applications, is to develop a systematic framework for the stability analysis and robust control of nonlinear infinite-dimensional systems. And we would like to have more. We would like to have not only separate theories for ordinary differential equations, time delay systems, parabolic equations, hyperbolic equations, etc. No, we would like to have a unified theory which will provide the universal tools which can apply for all such systems and to couplings of these systems. It should also cover both linear and nonlinear systems, and also it should recover the classical results for ODEs and time delay systems, which were developed several decades ago. In order to have a possibility even to approach this problem, we need a sufficiently general concept of a control system. And here is it. Under control system, we will understand a triple consisting of the state space X, input space U, and a flow map phi. We assume that X and U are Banach spaces and that the flow map phi satisfies the following axioms. First, we assume that for each initial condition X and for any input U, the corresponding trajectory is well defined for all positive times. Also, we assume that this trajectory is continuous and satisfies the so-called cocycle property, also called semigroup property. There are several further axioms which need to be assumed, but they are valid almost always, so I don't want to introduce all these formalisms. I will just tell that under reasonable regularity assumptions, ordinary differential equations, evolution partial differential equations with Lipschitz nonlinearities, time delay systems, and switched systems with infinite number of modes, etc. These all systems fall into this framework. So it is general enough to satisfy our needs. Moreover, actually, I have made here several simplifying assumptions for the sake of presentation. In particular, we don't necessarily need forward completeness for all our results. In most cases, local existence is enough. But okay, we have a sufficiently general concept of a control system. Now we need the stability notion, which will help us to analyze such systems. To introduce such a notion, we need auxiliary classes of comparison functions. We say that a function gamma is of class k infinity if it is 0 at 0 and is positive and increasing to infinity. A function of two real arguments is called KL function if it is 0 at 0 and increasing in the first argument, and if it decreases to 0 in the second argument. Now we can define the main notion for this talk. Following Eduardo Zonta, who has introduced the IS input to state stability in the end of the 80s, we will call the system input to state stable, or shortly ISS, if the norm of the trajectory can be upper bounded by a sum of two functions. Beta function, describing the transient behavior of the system, and function gamma, describing the asymptotic deviation of the origin. So here, beta is a KL function. In particular, the larger is the norm of the initial state X, the larger will be this bound. And on the other hand, if time goes to infinity, then this term vanishes, which means that asymptotically, the influence of the initial state goes to 0. And eventually, the system converges to the ball with a radius gamma of norm of U. So if we take U identically 0, then this term vanishes. And then the trajectory is upper bounded by beta function and so converges to 0, which means that for 0 input, the input to state stable systems are always uniformly globally asymptotically stable. If U is not 0, then there is no guarantee that we will converge to 0, and usually we don't do that. But as told previously, we will converge to the ball with the radius gamma of norm of U around the origin, which means that bounded inputs produce asymptotically bounded states. This fact that input to state stability unifies both stability with respect to initial condition, in the sense of Lyapunov, and also bounded input, bounded state property, this made this framework very mathematically appealing, because it is possible to study both these kinds of stability at the same time. But ISS does even more. In fact, if we think about finite dimensional systems, so ordinary differential equations, then input to state stability has revolutionized the control of nonlinear finite dimensional systems. It has made to the development of several techniques for robust control and observation of nonlinear systems. And it made possible to develop the controllers which will be robust against discretization of the input signal, delays in communication, several model dynamics, etc. And also it allowed to study efficiently the stability of the coupled systems, so of large-scale networks of dynamical systems. There are several monographs and survey articles devoted to input-to-state stability. So here I have put them in the chronological order, and in particular, I would like to attract your attention to this paper by Christophe Prieur and me on ISS of infinite dimensional systems, which is closely related to the topic of this habilitation. Okay, so since ISS was so successful for finite dimensional systems, it is natural to assume that it can be helpful also for analysis of infinite dimensional systems. And it can be the basis how we can solve our big goal to develop methods for robust control of networks of infinite dimensional systems. But there is a long way towards this goal, and I have put here some of the important intermediate stages. A good news is that some of these things are already done. In particular, those things which are in yellow color is where we have already a significant understanding. So I would say very good. So in particular, we know quite good the fundamentals of ISS theory for infinite dimensional systems. We know the fundamental properties of such systems. We know quite a lot about nonlinear time delay systems and about linear systems of, linear abstract systems. We know many things about Lyapunov theory and infinite couplings. But for example, we still lack understanding of nonlinear boundary control system, or how to control the nonlinear PDEs which are coupled via the boundary. So there is still many open problems, as I will tell in the end of this presentation. But now I would like to tell about what we already know and what we can do. And I will start with those things which we understand best, namely with the fundamentals of ISS theory. To do that, I would like to introduce one more notion. It is called uniform limit property, and here you can see the formal definition, but let me explain it in a bit in formal terms. So this property tells that there is some function gamma of class K infinity, such that if I take any epsilon neighborhood of this ball with the radius gamma of norm of u, and if I take here any bounded ball of around 0, then if I take initial condition in this ball, then I know that there is a time which is uniformly bounded, a fixed time such that for any initial condition in this ball, I will land within this epsilon neighborhood before some given time. Afterwards, the trajectory may diverge, but it will go back to this neighborhood within the same time. So this looks a bit like butterfly swimming. So if a swimmer makes a stroke, he goes out of the water, but then eventually converges back within some given time, which is bounded. Then it goes back outside from the water and then goes indeed inside. So in this like waving behavior, which is not really attractivity in the mathematical sense, but it is some weaker property, but still close to that. And it's called uniform limit property. In the theory of dynamical systems, there are related concepts, which are called weak attractivity, uniform weak attractivity, recursivity, etc. Okay, so now what we can do with this thing? And now we can characterize input-to-state stability to say what it really means. So, and now the system is, assume that we have any abstract control system as defined before, and assume that it has bounded finite time reachability sets. Then the system is input-to-state stable if and only if it satisfies this uniform limit property, this kind of butterfly swimming property, and if it is in addition uniformly locally stable. In dynamical systems theory, there is a well-known result that uniform global asymptotic stability for general dynamical systems on locally compact metric spaces is equivalent to global attractivity plus local stability. You can see this as a generalization of that result to the infinite dimensional systems which do not have any local compactness of the state space and which also have inputs. This result was first proved for finite dimensional systems in another formulation by Sonntag and Wang in the middle 90s. And it has led to major breakthroughs in the ISS theory. At the same time, for infinite dimensional systems, this problem was an open question for more than 20 years, even in the special case of time delay systems. And this was so until 4 years ago, Fabian Wirth and me have found a way how we should reformulate, how we should formulate this theorem in the right way and, well, and prove it. So, why this theorem is important? Well, it's important partially because of its mathematical appeal, just general, but also because it gives us several powerful methods for stability analysis. And I would like to mention in this talk 2 of them. One of them is the method of Lyapunov functions, which is basically the main method how we can show the stability and, in particular, input to state stability of nonlinear systems. And the second method are small gain theorems, which are essential for stability analysis of infinite networks or finite networks of stable systems. Let me start with Lyapunov functions. Lyapunov functions is a kind of generalizations of the energy concept in theoretical mechanics. So assume that we have some mechanical system and assume that we would like to study its asymptotic behavior. Then one of the ways how we can do that is to analyze the dynamics of its energy. If the energy has such a form, I mean, it's in the phase space, then if the energy dissipates, then under reasonable assumptions, one can show that the state of the system asymptotically converged to the state with a minimal energy, which is also the equilibrium point of this mechanical system. The idea of Lyapunov functions is to generalize this physical approach to much more general setting. So let me go to a formal definition. We say that a function V, a continuous function which maps state space X to non-negative reals, is a non-coercive ISS Lyapunov function if there are 3 functions, psi 2, sigma, and alpha of class K infinity, so 0 and 0 and increasing to infinity, such that 2 properties hold. The first of them tells that V is uniformly bounded from above by some function of the norm of the state, which is K infinity function, and also that V is positive definite in the sense that it is positive for all non-zero X and it is 0 at 0. The second property is a so-called dissipation inequality for Lyapunov function. It tells that the derivative of a Lyapunov function along the trajectory can be upper bounded by some of these 2 terms. The first term is negative, and it describes the dissipation of the energy due to internal dynamics. And the second term describes the influence of the input on the system. So if the state is large enough in compared to the input U, then this term dominates, and therefore the whole right-hand side here is negative. And this means that Lyapunov function decays, well, let's say energy dissipates. If, on the contrary, the input is large enough in compared to the state X, then this term dominates, and therefore this guy is positive, and therefore we cannot say whether function V decays or increases. We just don't know, but it may increase. If V satisfies even a bit stronger property, namely if it has, in addition to positive definiteness, also a uniform bound from below, then it is called a coercive ISS Lyapunov function. For finite dimensional systems, there is no difference between these two concepts. So if V is positive definite and X is Rn, then we can always find a function which bounds V from below. But in infinite dimensional setting, these concepts are essentially different, and non-coercivity is a big relaxation of the Lyapunov concept. Let us start with a basic result, which is rather classic. For ODEs, it was shown by Eduardo Zontag in his very first paper on ISS, and it can be extended to infinite dimensional systems without a big effort. And it tells that if there is a coercive ISS Lyapunov function, then the system is input-to-state stable, which tells that if we can find such a function, then we are done with the stability analysis, which is very good. The bad side is that coercive ISS Lyapunov functions may be hard to construct, and they also don't need to be the most natural Lyapunov functions in infinite dimensional world. So the question is whether we really need this coercivity. As a motivation of this question, let us consider just linear systems in Hilbert spaces. So here A generates strongly continuous semigroup on a Hilbert space X, and B is some bounded operator. Well, if you don't know what are strongly continuous semigroups, you may just think that this is an ordinary differential equation, but in some, and A is something like an extension of the matrix concept. So what we have here, one can show that this system is input-to-state stable if and only if there is a positive operator P, which is bounded operator, which satisfies the Lyapunov equation. And in this case, the Lyapunov function can be constructed in this form. Okay? So if we have such an operator, we construct this Lyapunov function V, and it is a certificate for input-to-state stability. But note an important thing. This operator P is just positive definite. It is not coercive. There is no uniform bound from below for this function V, and therefore it is only non-coercive Lyapunov function. So the classical method for construction of Lyapunov functions actually leads to non-coercive Lyapunov functions. Okay, well, this indicates that at least some non-coercive Lyapunov functions can be used to show input-to-state stability. There are also other results in theory of linear semigroups, in particular the Littmann's theorem, and those can be reformulated in a way that also other types of non-coercive Lyapunov functions are sufficient for stability of this system. However, all this is only for linear systems, and the proofs always use some kind of linear arguments. In particular, Banach-Steinhaus theorem and its invocation is quite essential in those results. And now, what we have done with Birgit Jakob, Jonathan Partington, and Fabian Wirth is that we have shown that actually existence of a non-coercive ISS Lyapunov function already implies input-to-state stability of non-linear control systems. However, we need also to assume that the finite time reachability sets of our system sigma are bounded and that the flow is continuous at equilibrium. So these are two properties which we need to assume additionally. And if they are satisfied, then actually non-coercive Lyapunov functions are enough to show input-to-state stability. Note that for linear systems, these two properties always hold, and therefore we have that any non-coercive Lyapunov function implies ISS, and this extends many classical results in the theory of semigroups. Well, let me just note that in this proof we cannot use linear methods just because we have nonlinear systems, and we cannot use the classical comparison principle arguments because we do not have coercivity. So a really very new type of the argument was needed, and it is based on the ISS superposition theorem, which I have showed previously. So it plays an essential role to justify the usage of non-coercive Lyapunov functions for study of stability. Okay. Well, so all these theorems which I have presented were direct theorems, that if we have a nice Lyapunov function, then we can show stability. But okay, I mean, maybe such functions just don't exist, right? So maybe there is no hope to search for such functions. And in order to start this search, we would like to know that such functions really exist. And this is the question of so-called converse Lyapunov theorems. And here I would like to present one of them. Assume that our infinite dimensional system has such a form. So currently we do not allow here in the most general class of systems, but this is still general enough. And if we take this class of control systems where f is Lipschitz continuance both with respect to x and u, then one can show that if this system is input to state stable, then there is always a coercive ISS Lyapunov function. In particular, we can always start searching for it. In the proof of this result, we base ourselves on the earlier result, which shows this fact for finite dimensional systems. Okay, so that was what I wanted to tell about Lyapunov functions. Now let us go to networks. And input to state stability is particularly strong for analysis of large-scale networks consisting of stable components. Assume that we have two control systems, sigma 1 and sigma 2, with the corresponding states x1 and x2. And they influence each other. The whole network we will call sigma. We assume that both these subsystems are input to state stable. So then such inequalities hold for some betas and gammas, and these gamma 1, 2 and gamma 2, 1, they describe the influence of subsystems at each other. And a fundamental result, which was first achieved in these two papers, is the following. If the composition of these two functions is less than identity, then the whole interconnection of these two systems is also input to state stable. And furthermore, if we know Lyapunov functions for these two systems, then we can construct a Lyapunov function for the whole interconnection. And it is very important for applications. This result was really shown for two systems. And then for n, for arbitrary finite number of finite dimensional systems, this was shown by Dashkovsky, Karafilis, Junggrove, and Wirth. Okay, so what I have told here is all about finite dimensional systems. And in order to solve our objective, we wanted to study large-scale networks of infinite dimensional systems with possibly of different types. So we need now to make this leap forward. And here we do it. Now let us consider an arbitrary network, which can be of finite size, but also of infinite size with infinitely many components. The subsystems here can be of any dimension and actually almost any type. So within our previous framework, let's say that can be ODEs, time delay systems, partial differential equations, etc. The couplings can be also here of different types. So we can couple the systems via the domain, like in population dynamics, or we can couple them from the boundaries in many engineering applications. Everything is okay as long as this interconnection is well-posed. And if we assume this well-posedness for the interconnection, then we can fully generalize the previous results, which I have just explained, to this very general setting. Furthermore, we can recover the results for finite networks of ordinary differential equations even under less regularity assumptions. So usually in these early papers, which I have mentioned, it was assumed that the right-hand side is Lipschitz continuance, and that was really used in the argument. And here we don't need that. We just need really the well-posedness of subsystems and well-posedness of the overall system. That's it. Furthermore, this result is new even for the special case of time delay systems. And even in this very special setting, it was open problem for 15 years. And here we show it in full generality. I don't want to go more into the details because there is quite a lot of formalism which has to be introduced. And I just go to the next question. But before that, I would like to summarize what we have reached till now, what I have explained. So we have considered a toolbox for analysis of input-to-state stability. We have seen superposition theorems which show the essence of input-to-state stability. We have seen the direct and converse coercive Lyapunov functions, which tell that we can use coercive Lyapunov functions for all infinite dimensional systems. We have also seen that actually under some minor additional assumptions, we can use even non-coercive Lyapunov functions for stability analysis. And this is a major step forward in generalization of Lyapunov function concepts. And also we have seen that we can develop the small gain theorems allowing to analyze large scale and even infinite networks of input-to-state stable systems. Still, you may ask how we can use all this machinery. I mean, it was quite abstract. So how can we apply this for some partial differential equations or delay systems? Well, that's a very reasonable question. In fact, we have indeed a big toolbox, but we use something. We have some assumptions in our theorems. And the very first assumption, which was hidden already in the definition of a control system, is its well-posedness. As I have started, I have spoken about a control system as a triple of the state space, input space, and a flow map phi, which describes the trajectories. So I already assume that we have unique maximal solutions for our systems. But usually when we talk about some dynamical or control systems, we don't have this flow. What we have are just some equations. And we first need to show the well-posedness of these equations in a certain sense. So to make this toolbox working, we need first well-posedness, but we need more than that. In all these results, we use some additional properties of the flow maps, such as possibility to prolong the solutions, or boundedness of reachability sets, or continuance dependence on initial states, or regularity of the flow map, things like that. And what we need now, we need a new toolbox which will help us to prove these properties, and then we can use this toolbox to prove the stability. So, and this is what we would like to do. But still, although we wanna go to specific systems, I still would like to have this second toolbox general enough. Therefore, this is the class of systems which I choose. These are semilinear systems in Banach spaces of the following form. So here we assume that X is a Banach space, and the space of input values is also Banach space. A generates a strongly continuous semigroup on this Banach space X, and B and B2 are some unbounded operators. And F is just some map, mapping, well, XU into the state space. So what we would like is to study well-posedness of these systems under some conditions on B, B2, F, and A. Okay. Well, let me mention that this class of systems was first studied probably by Natarayan and Bensman, but closely related classes of systems were studied also by other authors. So for the following, for simplicity of presentation, in the next slides, I assume that B2 is just identity. But just believe me that the results can be extended to general unbounded operators B2, which have some sort of admissibility. Okay, so our objectives are to derive sufficient conditions for well-posedness and some properties of the flow map. To do that, first let us look at a simplified problem. Let us forget about this nonlinearity. We just take the linear counterpart of that system. We set f to 0. And let us think what happens in this case. So, as before, X is a Banach space, A generates strongly continuous semigroup, and B is some unbounded operator from U to X, but we assume that it is bounded from U to X minus 1, where X minus 1 is the completion of X with respect to another norm. So it's not a big restriction. So actually, if the operator is not bounded from U to this space X minus 1, then it's really bad. So we don't want to have such operators, really. So we have several good news. Well, first of all, our original semigroup T generated by A can be uniquely extended to the semigroup T minus 1 on this larger space X minus 1. And what is good? In this space X minus 1, B is a bounded operator. And if so, we can write down just the solution for this system in this form. Well, it is called a mild solution of this system. And this is the usual variation of constants formula. So for ordinary differential equations, well, for linear systems, this T of T is just matrix exponential of A, right? And here we have the same thing, but instead of the matrix exponential, we have the semigroup T generated by A. So that's fine. So now we have a solution for this system. But this trick with going to X minus 1 comes at a price. This map phi in general lives in X minus 1, and this is not what we want. We want that if we start at X, well, in our state space, then we stay in the state space. But in general, we cannot show that. So to have that, we need some additional assumptions. So this is our system, and now we introduce the following concept. We say that our operator B is Q admissible if for any U from the space LQ, the corresponding trajectory lives in X for all initial conditions and all times. So basically, Q admissibility means the well-posedness of this system in the space of inputs equal to LQ. Well, and actually one can show using standard functional analytic arguments that if we have Q admissibility, then we have even such nice bound for this operator, for this term. And using this bound, one can show that input to state stability of this system with respect to LQ inputs is equivalent to exponential stability of the semigroup T and Q admissibility of B. Okay, so since this is just well-posedness, we can say that well-posed linear systems are input to state stable if they are exponentially stable. This is great. This basically gives a very nice criterion to study input to state stability of linear systems, because admissibility and exponential stability of semigroups are well-studied topics with lots of criteria how we can check it. And if we can check that, then we can check also input to state stability, which is nice. However, one thing is still missing here, because all these criteria which the researchers have developed, they are all for linear systems, right? And in the end of the day, we would like to go for nonlinear systems. And if we would like to study nonlinear systems, then we need some other types of criteria, and namely, we need Lyapunov functions. So therefore, what we would like to know is how we can study such systems with Lyapunov functions. Well, as I have told previously, such linear systems always, for such linear systems, existence of a non-coercive Lyapunov functions implies input to state stability. And now we present a converse result. If we assume that we have this system on a Hilbert space X, and we have an operator P which satisfies these properties. So these two ones we have already seen. They are needed just to ensure exponential stability. But if, in addition, these two properties hold, then this function will be a non-coercive ISS Lyapunov function for this system. So basically, we have shown how we can construct Lyapunov functions for such systems. Earlier, I have presented you a result for bounded operators B, and there was basically the same Lyapunov function. The trick is that if B is not bounded but just infinite admissible, then we need two additional conditions. And this is the essence of this result. Okay, well, I would like just to mention that if A is self-adjoint, we can even say what is our P, and this is this operator. Okay, so this is what I wanted to tell you about linear systems, but now let's go back to our non-linear setting. And we would like to analyze well-posedness of these systems. But before we analyze well-posedness, we need to define what is a solution. Well, and first of all, we need some assumptions. Well, first of all, we need that this operator B is infinite admissible, because otherwise we are out of business. The already linear part then is too bad. So we assume that if F is 0, the linear system is well-posed for L infinity inputs, and this is infinite admissibility. Also, we need the integrability of this nonlinearity for any continuance X and any U from L infinity. So we need that it is in L1 in the sense of Bochner integration. Okay, and now having assumed this, we can define what is the mild solution of this semi-linear system. And we say that a continuance function is a solution of this semi-linear system if it solves this integral equation, where the integrals are understood in the sense of Bochner. And now we have such a result. So if all the axioms of all the assumptions which I have told are fulfilled, and if in addition F is Lipschitz continuance, then the system is well-posed. It is a control system in terms of our abstract definition, and several further nice properties hold. So in particular, this means that under such assumptions, this class of systems which we have just considered falls in our general framework, and we can apply all our machinery which we have developed for analysis of ISS to this class of systems, which is great. Okay, well, actually the last point which I would like to say. Usually the linear theory and non-linear theory are considered as like two separate things. Each has its own methods, and basically there is quite few interaction between these fields. But I would like to say that at least for this input of state stability theory, there is quite a lot of this interaction, and linear theory helps quite a lot to analyze nonlinear systems. We have just seen that for well-posedness analysis, because we have used admissibility, which is basically a linear concept, in order to treat unboundedness of input operators. And we needed the fixed point arguments to treat nonlinearities. And we really needed to mix of both to have well-posedness result. Also, it helps a lot for stability analysis. Well, the people in linear systems theory have developed lots of important and strong tools how to analyze stability of linear systems, let's say based on the properties of spectra, resolvents, etc. But all of them are indeed only for linear systems. However, if we would like to develop Lyapunov functions, which is a right method to study stability of nonlinear systems, then usually for PDEs, we need to verify that a function is a Lyapunov function, we need to use some integral inequalities. And in order to develop those integral inequalities, we need to know very good the properties of our generators. And the spectral analysis of these properties is crucially needed. And this is where the linear theory comes into play, and where it gives us precise inequalities which we need, and with which we can get the tight results using our Lyapunov technique. So it's a very good start for analysis of nonlinear systems. Also, if we go to analysis of the networks, we have spoken about small gain methods. Just think that if we have infinite interconnection of dynamical systems, then this small gain analysis is based upon properties of ordered Banach spaces and positive functionals in them. And here again, the linear theory of positive functionals plays essential role. Well, clearly also linear theory helps at least partially for nonlinear systems with specific structure, which is not as good as linear systems, but quite good, like subadditive systems, bilinear systems, etc. So I'm really voting for the merge and interaction between linear and nonlinear world. Okay, so let us go for the summary. Today, we have discussed the tools for input-to-state stability analysis of abstract infinite-dimensional nonlinear control systems. We have seen how we can develop the direct and converse coercive Lyapunov theorems. We have developed superpositions theorems telling the essence of input-to-state stability. We have presented the major relaxation of the Lyapunov function concept, which are non-coercive Lyapunov functions. And there are also integral characterizations, which I have not presented, but which are also very nice. For evolution equations of quite general kind, we have also developed well-posedness criteria, and we have proved even converse Lyapunov theorems. Also, we know quite a lot about the properties of the flow map for these systems. Finally, if we go to stability of interconnected systems, then we can present here the small gain theorems for infinite number of systems, and we have also quite a number of related results on that. Okay, but still, we have reached quite many things, but we still have not got to our ultimate objective, which is the methods for robust control of networks of infinite dimensional systems. So what I have told before was all about stability analysis. Still something needs to be done, and this is here in green, and I hope that it will be yellow after some time. But let me tell about some important open problems. Well, first of all, we do not have converse ISS Lyapunov results for nonlinear and even linear boundary control systems, which are important. Also, although we know quite a lot about small gain theorems for infinite networks, even with nonlinear components, but we still need some strong applications of these methods in order to prove that they're really useful to people from engineering. The ISS superposition for time delay systems is a very important problem. So the theorem which I have presented, characterizing input-to-state stability as uniform limit property plus local stability, it works for time delay systems, clearly, because they fall into the scope of this general framework. But maybe for this type of control systems, this can be relaxed. Maybe. We don't know. And it's a very interesting problem, which is still unsolved. Also, it's really important to have a progress in event-based control for boundary control systems. This is a problem with which I have started my talk today. Also, study of monotone nonlinear discrete time systems would be very helpful for analysis of infinite interconnections. Well, and clearly it would be great to apply all this ISS machinery to study stability and robustness of important partial differential equations like Burger's equation or Navier-Stokes equation. So we can analyze many nonlinear systems, but let's say hard nonlinear systems are still beyond the reach of our technique, and we would like to improve it. So on this point, I would like to thank you all here online and offline for your attention, and looking forward to your questions.